Hello students. Welcome you to that new lecture of electric potential. We continue from where we stopped in the previous class. Today is not going to be a long lecture. It is going to be a very short lecture where we are going to discuss a very important topic. Why is it so important? We'll learn later in this class. So, today's topic is to know about equipotential surfaces. Okay, equipotential surfaces. Equipotential surfaces. Okay, equipotential. So you have fully understood the concept of potential, and from now on, we have added the small thing which means equal potential. Okay, so you can actually guess the definition from this term that some part of space or any surface that has the same potential across all its point. Okay, if it is a surface, okay, if it is a surface, so when are we going to denote it as an equipotential surface? When every point on that surface has the same potential. That means if A is a point here and B is a point here, so the potential at A is VA and the potential at V is VB, then when are we going to denote it as equipotential surface? When VA is equal to VB. Okay, that must be any arbitrary point on this space, on this part of the space. That may be any arbitrary point. Maybe you can consider the point here, point here, point here, point here, any place. Okay, if we consider these 2 points, then we have to consider that these 2 points have the same potential, or if we are going to consider these 2 points, then we have to say that their potential is same. That means there is no potential difference between those points. VA equal to VB. If this is so for every point on that surface, then you can actually say it is an equipotential surface. So you can actually write the definition of equipotential surface, that the surface or the part of the space where at all the points the potential is same. Okay, so write the definition. So what are equipotential surfaces? They can ask you the definition in any board exams or any viva. Okay, these are surface, or it is a surface. What is an equipotential surface? It is a surface where all the points have the same potential. All the points have the same potential. It is the simple definition of an equipotential surface. Okay, equipotential surface, here we are going to consider only electric potential, not gravitational potential. Okay, so it is a surface where all the points have the same potential. It is a type of a surface or any part of space where every point has the same potential. That means whenever you move through the surface, there is no change in potential. That's the important thing which I am going to emphasize more, that when you move through any point, or when you move through this point to this point of that surface, you don't, or that electric charge, okay, you can't feel electric potential. That electric charge will feel that electric potential. It will not feel any change in the electric potential. Okay, that is why it is an equipotential surface, and it is a very important, it is a very important concept. So I think you have written down equipotential surface and its definition. It is a surface where all the points have the same potential. Okay, VA equal to VB, or VA minus VB is equal to 0. There is no potential difference between any points on that surface. You can add this. There is 0. You can write no or 0. There is 0 potential difference. There is 0 potential difference between any points. Between any two points, there is no potential difference. There is no potential difference. So it is the definition of equipotential surface. You can write it as in like this. So this is my definition. You can create your own definition from your understanding. So until you understand, you just bring or try out this definition. And I hope that after this lecture you will understand it completely. So we have completed equipotential surfaces. So what is the need for equipotential surfaces? So what is the need for equipotential surfaces? We will know the need from these properties. Okay, from its properties. So I think I will rub this thing off and start to write down its properties one by one. Properties. So what is the first property? You can name it as 1. What is the first property? That for a charge that moves through an equipotential surface, work done is 0. Okay, no work is done. No work is done in moving. No work is done in moving a charge from one point to another on an equipotential surface. Equipotential surface. So just understand from the statement, if there is an equipotential surface and you have to move a charge through any 2 points on that equipotential surface, you need not do any work. Net work or work done is 0 in moving that charge. Okay, so this is a simple definition. I think it's showing. Yes, it is. So let us try to draw it. So if it is a surface, okay, this is a surface, it is an equipotential surface. So no work is done in moving a charge. Okay, you need to write it as test charge first of all. Okay, test charge. Why test charge? Because it has very small dimensions. Okay, its other dimensions can be ignored, like its mass. If we are going to consider a massy object, that object has a mass, then we need to do some work. The mass is more as compared to the charge, then we need to do some work. That's why we are including this test term. So let A and B, those 2 points, let A and B be those 2 points as we have drawn earlier. It is A, it is B. We are taking the test charge. Let the test charge be Q from A towards B. So it is moving a distance dl. Electric field is like this. Why electric field is like this, I will explain it later. So let A and B be those 2 points. So work done in moving. So work done in moving the test charge from A to B is equal to Q naught times VA minus VB. Okay, you can, okay, VB minus BA. You can name it like anything. Okay, since it is an equipotential surface, that means VB is equal to VA, and this term is equal to 0. This term is equal to 0. So work done in moving a test charge, our an equipotential surface is 0. So you can see the thing. So now let us move to the second property. It is also an important property. I assume that you have drawn it because I am going to rub it off. So I am rubbing it off. Now it is time to explain you why this electric field E is like perpendicular to the surface. Okay. So we are interested in this property. So what is the second property? Electric field is perpendicular to the equipotential surface at all points. So electric field is perpendicular to the equipotential surface at all points, which I drew the diagram earlier. So it is a surface, and electric field at any point here is perpendicular to it. At all the points it is perpendicular to the surface. Why is it so? So if it makes an angle, okay, let us consider that this is a surface and it makes an angle with the surface. Okay, this angle is theta. Okay. So you can actually see that this vector has a horizontal component and a vertical component. So in moving Q from this point to this point, that means Q, there needs to be a work done because there is some electric field on that surface. Now if we consider that electric field is perpendicular to the surface at all the points, it has no such parallel components to the surface. Okay, that's why we need not do any work. So at any point on that equipotential surface, electric field is perpendicular to the surface at all points. So I assume that you have understood. This is why, because as it makes an angle with that surface, it turns out it has two components. One is vertical component and the other is horizontal component. So in moving a charge from this point to this point, if electric field is pointing at this direction, then you need to do work against this electric field. Okay, so which is against the first condition of our equipotential surface. So electric field should be and should always be perpendicular to the equipotential surface. So I am rubbing this off. This is our second property. We shall be going to the third property. Third property is also a simple property. It is also related to these things. So it is points. Okay, it is points. I have to ignore this spot because at all points. Okay, those points should be in the equipotential surface. So it is showing now clearly. So the third property is about the relative distance between those equipotential surfaces. Relative distance between those equipotential surfaces. So we know that. Let me first of all try to explain this point and then I will convert it into a statement. E is equal to dV upon dr. E is equal to dV upon dr. Okay. So from this point, dr is equal to dV upon E. If it is a equipotential surface and it is also an equipotential surface, the potential difference between these points, okay, it's a constant quantity. That means you can write dr is inversely proportional to E. dr is inversely proportional to E. That means dr is the length. Okay, dr is that distance. This distance is here dr. So if E is strong, okay, if E is strong, that means E is bigger, which means dr is smaller. And if E is smaller, that means dr is bigger. This relative distance. So it says that if the field is very strong, the relative distance between those equipotential surface is very small, and if the field is very large or the field is very small, the relative distance between those equipotential surfaces is very large. Okay, so we are going to convert this statement into a, or we are going to convert this thing in this concept into statements. So what does it say? For a constant change in potential, dr is inversely proportional to E. For a larger field, the spacing between those equipotential surfaces is very small, and for a smaller field, the spacing between those equipotential surfaces is very large. So let us just convert it into a statement. So what does this statement says? The spacings between equipotential surfaces is very small for a stronger region of field. For a stronger field, okay, for a stronger field, yes, it is recording. The spacing between equipotential surface is very small for a stronger field, and vice versa. And vice versa. So from this point, you will have to understand that the spacing between electric equipotential surfaces is large for weaker fields. Okay, as you have learned from the electric field lines for a stronger field, the electric field lines for a stronger field are very closely packed, and for a weaker field, they are not so much closely packed. So in case of equipotential surfaces also, for a stronger field, the equipotential surfaces are very closely packed. That means the relative distances between them is very small. And in the opposite case, that is when the electric field or the field is weak, then the relative distances between those equipotential surfaces is very large. So we have to conclude the lecture today at this point. We shall be learning about equipotential surfaces, some diagrams of equipotential surfaces in later lectures. So up until this point, if you have any doubts, you can ask me in the comments, or I have provided my contact details in the description box. You can also contact me there. You can ask me numericals. So up until then, practice more. Take care of your health. Okay, see ya. Thank you.